All right, guys, welcome to your Unit 5 Quiz 2 Study Guide help video. So, question number 1, the graph below is of f prime, and we want to identify the intervals of increase and decrease for f. So, we have to remember that f increases when f prime is positive, and f prime is positive when the graph of f prime is above the x-axis. And so in this case, this is the graph of f prime, and it's above the x-axis on these intervals here, which are negative infinity to negative 2 and 2 to infinity. The reverse of that is true now. F decreases when f prime is less than 0, and f prime is less than 0 when the graph of f prime is below the x-axis. And so we could see that's occurring here, and that's on the interval from negative 2 to 2. Okay, so that'll be one of your questions there. Let's go ahead and move along. Make this one a little bit smaller. Sorry, it's going to be a little bit tiny. All right. So for this question here, I'm giving you the graph of a function g. Now understand, this is g. This is not a graph of g prime. This is g. Okay. So in this case, g is the slope. I'm sorry, g is the y value. G prime is the slope. And g double prime is the concavity. All right. So we're going to fill in each of these blanks with greater than, less than, or equal to. So let's start off with g of negative 4. That's this point right here. Now g is the y value. So what's the y value at that point? Well, it's negative 5, so that's less than 0. G prime of negative 4 would be the slope at this point. Now you guys can see the slope is positive there because it's moving in an upward direction, so we're going to put greater than 0. And then finally, g double prime is the concavity. As you guys can see, from here to about here, that's all concave down. And since it's concave down, that would mean that g double prime is less than 0. Let's take a look at another one. Part B, let's do 1. So for g of 1, that would be here. At that point, the y value is negative, so that's less than 1. The slope would be 0, so that's equal to 0 for g prime. The concavity at that point would be concave up, so that would be a positive second derivative. Let's take a look at part C. We're at negative 2. So at negative 2, the y value for that point is positive, so greater than 0. The slope is flat there again, so that would be equal to 0. And the concavity is concave down, and so that would be less than 0 for the second derivative. And it looks like we have another one here. Negative 1.5. Negative 1.5 is here. As you see, the y value is positive there. The slope, that's a downward going slope there. So I would say g prime is less than 0 since we have a negative slope. Now, g double prime is 0. And the reason for that is because at that point I would say our function is probably going from concave down to concave up. And so at that point, that would be like a point of inflection, so the second derivative would be 0. Let's go ahead and take a look at, oh, that's it. I thought I had another one. All right. So hopefully that was helpful. Let's go ahead and take a look at our next one here, number 3. Actually, I'm not going to do 3. I'm going to do 4, and then I'll let you guys do 3 on your own for extra practice. The answer will be on the answer key. All right, so we're being asked to find the relative min and the relative max. So first of all, we're going to go ahead and recognize that this is a polynomial, so there's no discontinuities. We don't need to worry about any of that sort of stuff. But we're going to go ahead and start off by finding our derivative. We set that derivative equal to 0. And then we're going to solve. You can use quadratic formula. I like to use factoring. In this case, I would factor out an x. You set each factor equal to 0 and solve. This one's already solved. This one, we would have to add 8 and divide by 3. And so we get x equals 8/3. These are critical values, and they are possibly relative extrema. To see if they are relative extrema or not, we're going to do our number line test. I'm going to put 0 here. I'm going to put 8/3 here. And I'm going to find the derivative and plug a number in from each interval. So for less than 0, I'll do -1. For between 0 and 8/3, 8/3 is about 2.6 approximately, so I'll pick 1. And anything after that, I'll plug in 3. Right? So if I were to plug in -1 into my derivative, or you can use the shortcut I shared with you guys in class with using the factored form, I would end up with a positive outcome here. I would end up with a negative outcome here and a positive here, which means that my function would be going up, then down, then up, making this point a relative max, and this point a relative min. And it says find the points, which means they want the x and the y values. These are the x values. And to find the y values, you simply plug these into your original equation. If you were to plug 0 in there, you would get 4. So there's one of our answers. And I would use my calculator to plug 8/3 in up here to find the answer that goes with that. And I would end up getting -148/27. Okay. Now, if you're doing it on your calculator and you end up getting a decimal, you can ask me. I'll show you how you can change your decimal into a fraction in class on the calculator. Or you could just look at the answers and see which ones, what fractions would give you the same decimal that you had. It's your choice. But there you guys have it. So you will be asked to find a relative min and max. The next question we'll go over is number 6. We're being asked to find intervals where a function is increasing and decreasing. So to do that, we're going to go ahead and find our derivative. And for this particular problem, the way we'll do the derivative is with the quotient rule. So we'll do the low d high minus high d low. Draw a line, square below. For these exercises, you will need to simplify the numerator. So I'm going to distribute the 2 there. Multiply those as well. And then we're going to combine our like terms here to get our simplified version of the derivative, which is 4x squared minus 16 over 4x minus 8 squared. and that's supposed to be 16x, by the way, I just realized. All right. So now we're going to find our critical values. Critical values are where the derivative is 0 and also where it's undefined. It's equal to 0 when the numerator is equal to 0. It's undefined when the denominator is equal to 0. So let's start off with the numerator. I can factor out a 4x there. Set each one equal to 0. I get 0 is a critical value. And I get 4 as a critical value. We're also going to set the denominator equal to 0. You don't need to include the square, just the part that's inside the parentheses. Let's go ahead and solve that one. So I've got 3 critical values here, which means I'm going to set up 3 intervals. So we're going to have 0, 2, and 4. And we're going to be plugging in a point to our derivative. For each of those intervals. So I'll plug in -1, 1, 3, and 5. I'll be plugging it into this guy here, and we'll see if we get. Once again, you could do the shortcut method, especially if you wanted to rewrite this top a little bit in its factored form, like we already did earlier. You could write it like this, and it might be a little bit easier. And that way you don't have to actually get the numbers. Another thing in this case to remember is that since the bottom squared, it's positive, and it really won't be affecting the outcome at all. It's just the top that will determine whether it's positive or negative, because the bottom will always be positive because of the square. Now those are just some suggestions to make it faster. If that's all confusing to you, just plug the number in, get an answer, and then see if it's positive or negative. But nevertheless, if you plug those numbers in, here's how it'll turn out. All right, and there it is. Now, notice that it doesn't do what we're used to, especially with polynomials. Usually it just kind of goes back and forth, positive, negative, positive, negative. But this one, we have positive, negative, negative, positive. That's kind of interesting. The reason for that is because this function has a discontinuity at 4x minus 8 equals 0, which we already solved. We got x equals 2. So this is actually not a critical value because it's a point where the function's undefined. And in this case, the reason for that is because this function actually has a vertical asymptote there at 2. So just some extra information. It actually isn't necessary to know that to get the answer to where it's increasing or decreasing. But that would be helpful to be aware of if you're trying to find maxes or mins, because if this point is not an actual value on your function because it's undefined there, then it couldn't qualify as a max or min. But we're not looking for that this time. We just want to know where it's increasing or decreasing. So I see that on this interval we're going up. I see that on this interval we're going in a downward direction because the slope is negative. I see that on this interval we're going down again because the slope is also negative. And I see that on this interval over here we're going up again. Okay, so we are ready to write our answer. Where is this function increasing and where is it decreasing? It's increasing on this interval here, which is negative infinity to 0. It's also increasing on this interval here, which is 4 to infinity. The function is decreasing on the 2 intervals in the middle from 0 to 2 and also from 2 to 4. Okay? And so that's how we will identify where a function is increasing or decreasing. Moving on to number 8. Now we're being asked to find where a function is concave up and concave down. This is going to be pretty similar to what we just did. It's just that we're doing it with a second derivative. So we need to start by finding our first derivative. And then we proceed to find our second derivative. We're going to set that equal to 0. And we're going to factor once again. All right, so I noticed that the three numbers present there can all be divided by 6. So I'm going to take out a 6. But I also don't like having a negative in the front like that, so I'm going to divide out a -6, which will change the signs as we divide. Next, we're going to go ahead and factor that trinomial there. Box method. What times what makes 2x squared, and what times what makes -1? Let's see. I'll try 2x and x. I'll try 1 and 1. And the question is, which one of those ones is negative? I'm going to try that one. Let's fill in our box. These should add up to make the middle, which they do. So we're in good shape. It's x plus 1 and 2x minus 1. Then we're going to set each one of those factors equal to 0 and solve. All right, so these are possibly points of inflection. They're only points of inflection, though, if the concavity actually changes at those points. So now we do a number line test to see if the concavity, in fact, changes there. So we have a -1, and we have a 4. And since we're doing concavity, we're plugging it into the second derivative this time. I'll plug in -2, 0, and 5. Once again, I think it's a little bit easier to use the shortcut I showed you guys in class and use the factored form. Or you could just plug it right into the original second derivative and just get a number. But if you were to plug in the -2, the 6 here would be a negative. Plugging a -2 into this first one would give me a negative, and plugging -2 in would give me a negative. So I'd have 3 negatives, which would make this a negative. If I were to plug in 0, I would end up with a positive. And if I were to plug in 5, I would end up with a negative. And what that means is that on the interval from -infinity to 1, we have a concave down. On the interval from -1 to 4, we have a concave up. And then on the interval from 4 to infinity, we have a concave down. And so, how we write our final answer here will be as follows. There it is. All right, so here is number 7. Being asked to find concave up and concave down. So, just like number 6, we're going to start by finding, it's going to be a lot like number 6, we just need to do it with the second derivative. We take the first derivative. We take the second derivative. And then we're going to set that equal to 0. That's all. Now in this case, I'm going to try to factor a little bit, but it's not going to factor all the way. That can happen sometimes. So I'm going to take out a 4. And this does not factor. So we need to solve that a different way. You could use quadratic formula. This is your A and this is your C, but I think that's a little bit extra work. Whenever you have a quadratic equation that looks like this, where you just have an x squared term, all you need to do is get the x by itself. So this is the strategy I'm going to be going with this time around. But like I said, quadratic formula works. The thing you have to remember about this is that when you take the square root, you do get a positive and a negative answer. Now, on your test, they're not going to leave the answer like this if you do have one like this. First of all, they're going to rewrite it. You're going to simplify it. So the first step to do is to separate them. The next step is to rationalize. We don't like square roots in the bottom, so I'm going to multiply the top and the bottom by the square root of 3. That makes the top become the square root of 6 and the bottom becomes 3. So it'll be written like this on your exam there. Okay. And those are my only answers for that. Now, what are those two values? Square root of 6 over 3 and the negative square root of 6 over 3. What are they? Well, these are possibly points of inflection. They will be points of inflection if the concavity changes at those points. So we have negative square root of 6 over 3, and we have positive square root of 6 over 3. And we need to pick some numbers to the right and left there. Now, those are weird numbers. So what you can do is you can kind of estimate this. What is the square root of 6? Well, it's not quite 3, but it's more than 2. So we have a number here that's somewhere between 2 and 3, and it's being divided by 3. So it's almost negative 1, but it's probably not quite a negative 1. So I would say we'd be pretty safe if we just chose to plug in a negative 2 here. Here we could definitely do 0, and here we could do 2. So just estimate the value, or if you're lucky enough to be using a calculator at that time, you can just plug it in your calculator and turn it into a decimal, and you'll see what the actual thing equals. But anyway, let's go ahead and plug these numbers into our second derivative. I like to use the factored form. If you were to plug in negative 2, you would get a positive outcome. If you were to plug in 0, you would get a negative, and 2 would give you a positive. And so what that means then is, make some room. We have a concave up here, concave down here, and concave up here. So concave up would be this interval, which is negative infinity to negative square root of 6 over 3, as well as this interval, which is square root of 6 over 3 to infinity. Concave down would be this interval, which is from negative square root of 6 over 3 to positive square root of 6 over 3. So the last part of our study guide here is to work with that FRQ question, 2005 question 4 in your blue books, which was assigned earlier to you, where you need to be able to identify critical values, relative, max, min, and points of inflection. So I'll show you that in the next slide here. All right, guys, so for this FRQ, which is in your blue books, it's FRQ 2005, and it's question number 4. Now, I'm going to do part A and B, but when I do part A, I'm going to do a little bit more than they're asking for, just because, you know, on your quiz, I might be asking us to find a little bit more than that. So let's go ahead and get started. So they give us a table here. They're telling us that the function is twice differentiable except at x equals 2. So they put D and E here for does not exist. So they want us to use this table for part A from 0 to 4. That means we're going from beginning to end. They want us to find all the values of x for which f of x has a relative extrema. That means max or min. And then finally after that, we want to justify our answer. Okay. Now, there's two ways that you could identify relative extrema. One way is with the first derivative test. Another way is with the second derivative test. I think I'm going to go ahead and go with the first derivative test. So the first thing we're going to do is we're going to look for where f prime is undefined and where f prime is equal to 0. So we're going to look at our f prime row, and I see a couple of places here where f prime is 0 or undefined. Okay? Now, once we find those places, we look to the left and right of each one. So for 0, to the left it's positive. Actually, but before I go any further, we should probably put the x value. The x value at that point is 1. So for this one, if you want to put a little number line here, we have x equals 1, and we also have x equals 2. These are our two critical values, possibly. Okay? So x equals 1 and x equals 2 are critical values because that's where f prime is 0 or undefined. Now, if I look to the left of 0, it tells me that f prime is positive. F prime is positive. That means my graph is moving in an upward direction. If I look to the right of 0, it's still positive. So my graph is still going in an upward direction there. After the 2, however, it's negative. Okay? So, what does that mean? That means that this value is neither a relative min or max, but this number is a relative max. Okay? So, we would say there is a relative max at x equals 2. And I wonder if they want the y value. It says find the values of x. So we'll just put x. There is a relative max at x equals 2 since, and here's how you write your explanation. At that point, the slope goes from positive to negative. Actually, we'll say since f prime changes from positive to negative at that point. Okay. So, now, you don't have to show this work. You can, but you don't have to on your FRQ when you do this. What matters is this statement over here. You're going to be getting 1 point for identifying where your relative max is at, and you get 1 point for your explanation. So this is a 2-point question. All right. There are no relative minima on this, so we won't include that. Right. Now that's the that is the question that was being asked on part A, but Mr. Bailey's extra notes here, we get to call this. This will be helpful on your quiz. I'm going to find some other things, okay? So we found the relative extrema. We found the relative min and max. That's one thing that you'll need to be able to find. Another thing that you need to be able to find is critical values, and we actually already did that too. Critical values are those places where f prime is 0 or undefined. So that was these points here and here. And critical values are the x values that go with that. So the critical values are x equals 1 and x equals 2. This is 1 since at that point f prime equals 0. And this is a critical value since at that point f prime is undefined. And so those are your critical values. Now technically, just so you guys know, the point has to exist also. So for instance, even though f prime is undefined, the point exists. The point is 2, 2. Now if there was no y value here, that would mean the point doesn't exist, and that is not a critical value. But since both of these have y values, they're both candidates for critical values, and this one is a critical value because f prime is 0. This is a critical value because f prime is undefined. So we've learned how to find relative min and max. We've also reviewed how to find and explain critical values. Once again, you get 1 point for your answers, and then you get another point for your explanations. So that's kind of how this works. 1 point is the answer, 1 point is the explanation. All right, now another thing that you could be asked to find instead of critical values is you could be asked to find points of inflection. All right. A point of inflection is a place where your concavity changes from positive to negative or from negative to positive. In other words, the second derivative changes from negative to positive or positive to negative. But once again, the point has to exist. So here's a place where f double prime is 0, and if you look to the left and right, it changes signs at that point. So that's a point of inflection. At that point, x is equal to 1. Let's see if we can find another one. Here, it does not exist. We also change from positive to negative. So it's another switch there, and that is at x equals 2. And then, if you notice right here, we have another place where it goes from negative to positive, and that's at x equals 3. So there are 3 points of inflection, and right there, that would be worth 1 point, identifying all of the points of inflection. It's anytime you find a place where the concavity changes from negative to positive or positive to negative. Now for these, the answer could be the same for all of them because they all have the same explanation. And here's the reason. These are all points of inflection since f double prime changes signs at these points. So that's your explanation. You don't have to write a separate one for each one like I did over here. And the reason for that is because they all have the same explanation. Technically, this one changes from negative to positive. Technically, this one changed from positive to negative, and this one's negative to positive. But it doesn't matter what direction they change in for points of inflection, just so long as it changes. Over here, the critical values, I had to give separate explanations because they were for different reasons. This is a critical value because the derivative was 0. This is a critical value because the derivative was undefined. Okay. All right, let's go ahead and do one more thing that for Mr. Bailey's extra special notes here on the side. You guys need to do intervals of concavity. So concave up and concave down. Now that's going to be pretty simple because concave up happens anytime you have a positive second derivative. All right, so that would be, for instance, here. Oops. That's a positive, and that's a positive. So the intervals are from 1 to 2, and also from 3 to 4. Okay, so we would say it's concave up on 1 to 2 and 3 to 4 since f double prime is greater than 0. Concave down is the opposite. You can see here that the second derivative is negative there. And it's also negative here, by the way. And it's negative here. All right, so for this first interval here, we would say 0 to 1, but for the 0, I'm going to put a bracket. 0 to 1, but the reason I'm going to put a bracket on the 0 is because the 0 is included. At that point, it's still concave down. Whereas here, this is an open parenthesis for the 1, and at 1, it's no longer negative, so I wouldn't include this one as being concave down at that point. Okay. Now, just so you guys know, I was told a while ago that AP doesn't care whether you use brackets or parentheses, so I won't care either, but I'm just being technical here. The other interval here is from 2 to 3. And the reason for that is since f double prime is less than 0. Okay, so once again, you wouldn't, I don't think I would ask both of these questions, but regardless of which one you answer, you get 1 point for the answer, and you get 1 point for your explanation. Okay, and that's it. So that's how all these work. 1 point for the answer, 1 point for explanation, and once again, you guys are going to be asked on your quiz to find a few different things. Critical values, relative extrema, points of inflection, and concavity. All of them you get 1 point for an answer and 1 point for an explanation. So regardless of which one you get 1 point for your answer and 1 point for your explanation. That's how they all work. Okay. Now we're not quite done yet with this question. I'm going to go back now to finishing the FRQ. It says, on the axis provided, sketch the graph of this function. So now I didn't provide a graph here, but in the original problem we did. All right, so I noticed that my x values are going from 0 to 4. So 0, 1, 2, 3, 4. I'm noticing that my y values go from -1 up to a +2 is the max. So 1, 2. So first of all, let's go ahead and do our points that are defined. So we have the point 0, -1, which would be, oh, I missed that -1. 0, -1. We have 1, 0. We have 2, 2. And then we have 3, 0. Okay, so the points that we have. Now, notice that in between x equals 1 and 0, we have a negative slope. So between 0 and 1, we have a negative slope. I take that back. We do not have a negative slope. I was looking at the wrong one. This is for f. We have a positive slope between 0 and 1. When you're looking at slopes, we look at this row. So for the f prime row, that's our slopes. So between 0 and 1, we have a positive slope. So I'm just going to draw a line that connects those with a positive slope. Between 0 and 2, we have another positive slope. And then between 2 and 3, we have a negative slope, it says. And then between 3 and 4, we have a negative slope. All right. Now we're going to do our concavity. Now I'm noticing that from 0 up to 1, we have a negative concavity. So it should be concave down. So now I'm going to come over here. I'm going to take this, and it needs to be concave down with a positive slope. So that would look like this. Concave down, but still a positive slope. So I'm going to bend it like that. Next, between 1 and 2, we have a concave up. So I still want a positive slope, but now I need to bend the line so that it is concave up. So now we have that shape going on. Next, we have concave down from 2 to 3. So this little interval here needs to be concave down. Now notice the sharp turn here, and that makes sense because the first and second derivative don't exist at 2. So we have a cusp. Finally, between 3 and 4, we have a positive slope. I'm sorry, not a positive slope. We have a positive second derivative, which means that we're doing concave up. So here's our graph in its final form. So basically, you start off with your y values. After that, you sketch your slopes, but you're going to have to go back on your last step and bend those slopes so that they have the right concavity. All right? And that will be it for that.